Ta-da. All right. I'll still have a freak out mid class, but did I? Okay. So, couple of things I wanted to, just a reminder. All right. Either you're welcome to join the 8 a.m. Zoom meeting because it's just on Zoom tomorrow, or after that, I'll post the recording once it's done doing whatever it does before it's sent to me. And then I'll post that recording. So then you can watch the recording during our class time or whenever you'd like over the weekend. Oh, how fun. Only the 8 to 8:50 section will be live, but I know because you're not in that section on Zoom, so you might not be able to make it. So you can either join there or join then, or, oh, what's going on here? Or watch the video anytime. Okay, so in case you're not too familiar here, I'll do this here. So from our Moodle page, in case you haven't, tried it or whatever, there's the Zoom classroom link here. So you can join here. There's also the meeting ID. There's no password. I use the same classroom or the same Zoom room for all my classes. It's like my room. So that's how you join. Or if you want to watch the videos afterwards, then this is where they'll be posted. In case you hadn't noticed, I've posted quite a few, assignments. I know, right? How rude. So just to keep an eye out, I do try to remember to add them to our calendar. It doesn't happen automatically. So there's assignment 5, which I know a lot of people have been working on, but then there's assignment 6 from last week. And then I also posted assignment 7 on conditional probability. Oh boy, what fun. Right, so just keep an eye out for that. And then also here, I've made a note. Oh, not that far. We probably won't talk about the geometric distribution, which is what we're supposed to be doing. We're probably just going to continue with the normal distribution because it's way more important. And I didn't quite get through all of it this morning. So I doubt I'll get through all of it with you guys. Okay. Good. So that's what's going on with our Moodle page, I guess. For some review, we didn't quite finish the example from last day, that big tree diagram that we were working on, right? And so from the tree diagram example, and I'm gonna do this. First, I'm gonna copy this. Oh, wait, wrong one. Okay. Right, we had that parking garage one. And we spent some time and we set up the tree diagram. Comme ça. Paste, okay. There. Okay, so we had this tree diagram, right? And so here's where, this is all from last day. Okay. What we said was, okay, well, I can multiply down each branch, right? And I can find the probability of there being an athletic event and the garage being full, right? So as I go down the branches, I'm saying and, which is a clue that I'm going to be multiplying. So at the end of each of these branches, I find those joint probabilities, right? It being a sporting event and it being full, or sporting event and it's not full. And once we've outlined all those possible outcomes, then that's everything that could possibly happen, right? And so now all these probabilities should add to 1, right? And so here, I'll just make sure the total must be 1. I did not go through and do that, but hopefully that's the case. I don't think I rounded, so it should be fine. Okay. And if it's not, I'll have to go through and fix something, but let's assume the total is 1. Okay. There's a question here that we were trying to answer. So usually what I do is I just go through and I set up all these probabilities in all these branches, as well as the probabilities at the end of each branch, because then I can solve whatever problem I want, right? And so, for example, what's the probability of the garage being full, right? So let's kind of stray a little bit here. The probability that the garage is full, that can happen a few different ways, right? It's full here, or it's full here, or it's full here, right? And so there are 3 ways that the garage can be full, right? And so now it can be an athletic event and it's full, or a sporting event and it's full, or nothing, and nothing, no events. Oh, that's cleaner. No events and it's full, right? So what I would have to do is, that's the probability of A and F plus the probability of S and F plus the probability of N and F. Which I've already calculated here, so I can just steal those, right? You don't even really need to write this out. This is more me filling in the notes so that they're not incomplete when you go back and look them over, right? And so if you wanted to, you could just jot down the probabilities right away. But A and F is 0.0875. S and F was 0.14. N and F was 0.0225. I did not bust out my calculator, but I can. 0.0875 plus 0.14 plus 0.0225 puts me at 0.25. So the probability that the garage is full is 0.25. We wanted to find what's the probability, oh, sorry, if, Jose comes to campus and finds the garage full, right? So we know the garage is full. What's the probability that there's a sporting event, right? So really what we want to do here is first structure this as a conditional probability, right? Because we've been told that, okay, we know the garage is full, right? And so we want to find the probability that there's a sporting event given that the garage is full. Right? That's kind of tricky because whenever I read these, I always want to put the given thing first, but you have to remind yourself that, okay, the given is that vertical bar, right? And so given, and then the information that's given goes last, right? Because now we can find the probability of it being a sporting event, given that the garage is full. Remembering that the probability of A given B is the probability of A and B divided by the probability of B. Oh, I forgot to show off to you guys before we dig into this one here. I have to show off my handiwork. I did it. The conditional probability, if you start it, I attach the formulas so you can have them like that, or in the, well, on the iPad, it looks a little weird, but you can just have the little formulas ready. Okay, so that's how it'll be on the quiz. Okay, notice that once I go to this bigger one, what I've done, so you've already seen the descriptive statistics section, that's from quiz 1, and now I'm adding the probability, right? And so for each new section that we add, I'm going to add to the formula sheet until eventually we're going to have a full formula sheet. But this way you're able to stay focused. Okay. And so of course on this formula sheet, well, I don't have a pointer on here, but right, we've got the conditional probability of A given B is the probability of A and B over the probability of B. Aren't you so impressed that I did that? I know. Maybe it's not that impressive if you didn't know what it required of me. Okay, so mapping, the S becomes A and the F becomes B, or however you want to think about it, right? You're just going to map these. And so the probability of S given F is the probability of S and F divided by the probability of F. Hey, we have all these probabilities, right? Because we already said, okay, it has to be a sporting event and it has to be full. That happens with a probability of 0.14, right? And so now I can replace this with 0.14 divided by, oh, surprise, surprise. That's why I wanted to find the probability that the garage is full, because we need it here, right? The overall probability that it's full, regardless of what event is happening, right? And that probability is 0.25. And now, dun, 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 divided by 0.56. And this is the end of the page, so I'm gonna just kind of write the answer off to the side, but, or maybe I don't even need to. I would just reword the question as an answer, right? If Jose comes to campus and finds the garage is full, the probability that there is a sporting event is 0.56. Sure, I can write that down. Give myself a little bit more room here. How did it start? If the garage is full, the probability there is a sporting event is 0.56. And with that, we finish this kind of traditional probability section. Gets a little bit confusing because we're going to talk about probabilities for the rest of the term, but not like this. Okay, that's it. Okay. Woo. So good. Conditional probabilities are, of course, very difficult, right? But you'll find that the tree diagram is helpful, right? Especially, so I posted that conditional probability assignment. There are two questions that I'm thinking of in particular that are very, very hard the first time that you try them, okay? I think it's an HIB one and a voting one, okay? Those are very difficult, but first thing you're gonna do is set out your tree diagram, right? And then all those probabilities for the tree diagram you'll be given, and then you'll kind of go from there. So that's my clue for those. But just know that they are difficult, right? But assignments, that's what assignments are for, making you work through harder problems. Because usually what I end up doing on a quiz or on the final, if I've made you work through a hard problem, right, then I don't feel so bad giving you that problem with different numbers on a quiz or on a final, right? Because you've worked out how to solve it, right? It'll be different numbers, but I think that's fair. So it's worth kind of putting in the time and figuring out, how am I supposed to solve this thing? All right. Probability, done. As I'm about to say probability in the next 5 minutes. Okay, here we go. So section 4.1 is on the normal distribution. Finally, something that we're kind of back to things that we sort of know, right? What do we know about the normal distribution? Well, it's a shape, right? And so it's a shape and it looks kind of like this. Oh, like this. Okay. Right? If we have a normal distribution, then we said, okay, the most appropriate measures of center and spread are going to be the mean and the standard deviation. Great. Let's jot that down. So if we have a normal distribution, we use the mean and standard deviation as our measures of center and spread. As our measures of center and spread. Okay. So that means if I tell you that something follows a normal distribution, I'll also give you the mean and the standard deviation. So what I want you to do, as soon as you read, okay, it follows a normal distribution, first thing you're going to do is draw the normal distribution. Okay. Even if you have no clue what to do next, that's the first thing you're going to do. Next thing you're going to do is you're going to draw a line down the center, which is the mean. Okay. We're going to use mu for the population. Okay. And then somewhere off to the side, you'll say sigma equals some number, right? The standard deviation is some number. But until we've covered some other stuff, there's nowhere to put the standard deviation. So I just jot it down in the corner here because we'll need it, but it's just fine off in the corner. Okay. So the normal distribution shows us that values around the mean are more common, right? They happen more frequently, right? And then as we move further away from the mean, so out into these tails, right, the area gets smaller and smaller, right? And so out here in the tails, we have these rare observations. Okay. When we're talking about, okay, these are more common observations around the mean, and then we get these rare observations, how can we talk about that kind of more concretely? What we're saying is that the probability of being around the mean is higher, right? And then the probability of having these rare observations is quite small, right? And so the area under the curve here is a probability, okay? But not like we've been dealing with. So that's why I said I'm about to say probability again, right? But rare observations mean that the probability is low. Right, the probability of seeing these rare observations is quite low. Okay, so, right, let's write down that the area under the curve is a probability. The area under the curve is a probability. We know things about probabilities, right? Probabilities are between 0 and 1, right? They're proportions, but also the total probability has to be 1, right? And so therefore, the total area under the curve is 1. Yeah. What gets a little kind of crazy is that in theory, these tails go to infinity and negative infinity, right? They go and they go and they go and they never close, right, on the axis, because there's always a chance of this rare occurrence happening, right? But the probability is very, very, very low. Okay? And so here, I'll draw another one. I'm going to draw so many normal distributions. All right. What I just said was that these tails never close on this axis here. They go to, almost did negative infinity on the, mixed them up. Right. The tails, in theory, the tails go. So in theory, in applications though, there would be kind of a finite number of outcomes or possibilities, but in theory, the tails go to plus minus infinity, right? This is really just saying that anything can happen, right? You're just opening yourself up to it. Anything can happen. Anything can happen, right? But with an extremely small probability, right? But with an extremely small probability. So that's going to be important for later, right? You're going to find values, and we'll kind of get there, but you're going to find values that are way far out into the tails, and you're going to email me or message me and say, oh, this can't happen. And then I'll say, well, anything can happen, right? But the probability is very, very small, right? Okay, so let's, for completeness sake, I'll put the mean here, and let's just remember that the total area is 1. So that total area under the curve is 1. Okay. So a little bit of shorthand notation, right? Instead of writing out, okay, something follows a normal distribution with a mean of this and a standard deviation of this, we're going to have shorthand for that because that gets annoying to out. So to denote that an observation X, okay, so usually we just use X as a placeholder for this observation, follows a normal distribution with mean mu and standard deviation sigma. We write that X follows is shorthand by tilde. Okay. So this here is a tilde, and it means follows we use a capital N to denote the normal distribution. And then capital N and then bracket. So basically like function notation N of, and then we give it the mean and the standard deviation, right? And so mu is the mean and sigma is the standard deviation, which we separate by a comma, right? But you have to remember that the mean is the first one and then the standard deviation is the second one. Usually I get lazy and I don't write the mu equals this and the sigma equals this, although you can. Right. So, trying to think if I wanted to. Yeah, you know what? No, not yet. I've got an example, but I don't want to bring it in quite yet. There's some other things I want to talk about. Okay, so this is the shorthand, and sometimes the question will just be stated with the shorthand. So that's why you need to be able to read it, right? But once you get over this follows, then you're fine, right? That's kind of the tricky part. Okay. So what we're going to want to do is often we want to compare observations from two different distributions, right? And so my height compared to the rest of the population of females' heights versus, I don't know, some male heights, right? They would follow a different distribution, right? Still normal distributions, but different mean and different standard deviation, right? So we want to compare these values, right? And so what we're going to do is we're going to standardize these values. Okay? Did they say kitty, kitty, kitty?
Yeah.
I hope there's a cat out there. Or maybe there is, well, if there's a cat, I would want to see it. So maybe I don't hope there's a cat out there, because then I would have missed it. Okay, in order to compare observations from different distributions, what we do is we standardize those observations, Okay. So in order to compare maybe that's what I should start doing. Just during my breaks or whatever, if I'm walking down the hallway and there's a class going on, just be like, kitty, 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 kitty. So in order to compare observations from two different distributions, I'm going to say normal distributions. It works for all distributions, but because we're focusing on normal distributions, I'm going to say that normal distributions we need to standardize the values. So as kind of an exercise to prove to yourself that you already know this stuff, I'm just gonna give you formulas to attach to the things you already know, okay? Then I wanna bring in an example from the textbook here. Okay. Even without me giving you any other information, I think with enough time, you'd be able to solve this problem and essentially develop the formula. Okay. So classic example, SATs and the ACTs, I think are university entry exams in the States. I don't know, I've never written any of them, but right, they've got these kind of entrance exams, and there are two different exams, the SATs and the ACTs, and I get them mumbled. And they're on different scales, right? So you can write either one and then you apply, but how does a university take SAT scores and ACT scores and compare them, right? So that's what we're gonna do. So here we have the mean and the standard deviation of the SATs and the ACTs. Okay. The distribution of the SAT and ACT scores are both nearly normal. We'll keep that in our back pocket. Suppose Anne scored 1,300 on her SAT and Tom scored 24 on his ACT. Who performed better? Oh boy. Okay. Wheels are turning. How do I do this? How do I do this? Okay. I'll kind of hold your hand, walk you through it. Because you're probably leaning towards, okay, what if I took Anne's score of 1,300 and I don't know, maybe let's see how far she was from the mean, right? So take that distance, right? But then we know that there's a spread, right? The standard deviation of 200 versus a standard deviation of 6. So I need to take that into account somehow. So what if we figured out how many standard deviations each of these observations were from the mean? Oh, what? You just came up with that out of thin air? No, but with enough time, I think that's where people would, what we would end up doing. And that's exactly what we're going to do. Okay. And so what we're going to do is, I forgot to bring it in earlier. We're going to find the Z score. Okay. And the Z score is a standardized value. Okay. So what you kind of would have arrived at is officially called a Z score or a standardized score. Okay. So the Z score of an observation, and observations we denote by X, right, is the number of standard deviations, which is sigma. It falls above or below the mean, which is mu. So here's what we kind of walked through, right? I took this observation, so Anne's score of 1300, for example, I saw how far was it from the mean, right? I subtracted the mean of 1100. And then I had to take that distance of 200 into account with the overall spread, right? Which is the standard deviation. Yeah. So let's jot down some things here. So the Z-score, I know it says it in that blurb, but it doesn't hurt to say it again, because it's really important. The Z-score tells us how many standard deviations an observation is from the mean. Also called a standardized value. Also called a standardized value. Okay. So what we can do, right, if we want to know who performed better, right, what we can do is we can basically scale down these two scores and we can standardize them. And now all of a sudden they're on the same playing field and we can compare the two, right? And so if we kind of visualize these two distributions, right, we know they're nearly normal, so I know the shape, right? So first thing I'm going to do is I'm going to draw the nearly normal. And because that one was so good, I'm going to copy it. It's beautiful. I'll do SAT and ACT here. Yeah. I gave myself some room because I need to jot down the mean, right? So the SAT had a mean of 1100, which goes down the middle. And the ACTs had a mean of 21. And just down below somewhere, I'm just going to jot down the standard deviation of 200 and sigma is 6. Yeah. We're not really working with the curve yet. So if you wanted to just focus on this number line down below, that's totally fine. And just kind of ignore the curve for a little bit, right? So then what we would do is, okay, I've got Anne scored 1300 and Tom scored 24. So what if I kind of jot these down here? Remembering that this is the number line for the SAT scores, right? So then 1300, as long as I put it somewhere above the mean, right? Kind of recognizing that that's above the mean, you can put it anywhere because it's just to visualize the problem. And maybe what I'll do is I'm going to denote this by X Anne. X, remember, is an observation, but because I have an observation for Anne and one for Tom, I'm going to use a little subscript to denote which one is which. Sneaky. And then I know Tom got 24 on the ACT, which is also above the mean. So I'm going to put that there. right? If you wanted to just work with a number line for now, that's totally fine, right? And so now we can kind of visualize it and we can see, okay, the z-score is going to be the distance between the mean and the observation, right? And then how many standard deviations can I fit into that distance, right? So what we can do is we can calculate a z-score for each of these. Now, because I'm doing both kind of advanced, starting with 2 already, where we have to use a subscript, but maybe it's good. Maybe it's like a sink or swim situation. We'll get there. I'll show you one with just one observation. So a z-score for Anne then is going to be x for Anne minus mu over sigma. Which is 1300 minus 1100 over 200, which is 200 divided by 200, which is 1.00. Okay. We're always going to use 2 decimal places for Z, and the reason will become clear in a little bit. Always use 2 decimal places for Z, rounding properly. Right, not just chopping it off, but rounding appropriately. Okay. Yeah, like, wait a second. Yeah, up for 5. 4 and below, down. Okay, good. So what does this mean? This means that Anne scored 1 standard deviation above the mean, right? Is really what this says. Let's do Tom first. I will write that down, but not yet. So a z-score for Tom, I have to, oh, that made even more of a mess. Is the observation for Tom minus the mean. I mean, technically I should be putting which group they're from, but even I don't do that, and I'm pretty particular about this stuff. Tom's observation was 24 minus the mean, which was 21, and the standard deviation is 6. So 24 minus 21 puts me at 3. 3 over 6 is 0.50. Okay. So now, right, that means that Tom only scored half a standard deviation above the mean for his group, right? And so who performed better? Anne performed better, right? Therefore, since Anne scored 1 standard deviation above the mean, and Tom scored, should I be mean and say only half a standard deviation above the mean? Still above the mean, that's really good. Scored only half a standard deviation, I'll use the shorthand SD, above the mean. And performed better. So in order to compare values, even if they're on, different measurement scales or from different populations, if you standardize them, right, then we can just talk about how many standard deviations away from the mean were these observations, right? And so some kind of fun facts or little fun facts, LFFs, little fun facts. I don't think I've done an LFF in this yet. About Z-scores. If our observation came from a normal distribution, then when we convert it to Z-scores, then that's also going to be a normal distribution. So if our observations came from something like this, if the observations came from something centered on mu, and the standard deviation is sigma, then let's say I have an observation down here, and just as a general example, what happens when I standardize everything here is it basically shrinks down. So here, if we standardize, it's not really looking like an arrow, is it? How about that? So if we standardize, then I can steal this curve again, copy, line it up. But what happens is now this X becomes a Z, right? If we think about Z-scores, if I take the mean and I want to find how many standard deviations the mean is from the mean, well, that's going to be 0, right? So now all of a sudden, Z-scores are centered on 0, and the standard deviation, just as a rule, is 1. Because now it's on this, how many standard deviations away from the mean are you? This is called the standard normal distribution. The standard normal distribution, which we could shorthand as Z follows a normal distribution with a mean of 0 and a standard deviation of 1, right? Just as a rule. Or if you wanted to, I guess, maybe I jumped in too fast, but mu is 0 and sigma is 1, right? But usually we just write it like this. What's another thing? All the values, let's see here. All the values below the mean are going to have negative Z-scores, right? And so here, these will be negative Z-scores, while values above the mean are going to have positive Z-scores. Right? So that's why it's important that you do X minus mu, because otherwise your sign is going to be reversed, right? It's also a nice way to check in with, does your Z-score make sense, right? So when we drew these curves here, right, I know that 1300 is above 1100. Right, so then if I went through and I did my math and I had accidentally swapped these two, I would get a negative number, which would would kind of set off alarm bells, and I would say, oh no, but I know it's above the mean, so it should be positive, right? The value itself, right? The distance would be the same, but whether it's above or below matters. Okay. Okay. Good.
Why the notation of tilde and 0 and 1? Like, isn't the 0 always going to be there for me?
For Z,
Yes.
yes.
Okay.
So it's always 0, 1. So this one is established, but because it's Z, it's centered on 0 with a standard deviation of 1. So it's like a special case.
Okay.
Whereas if we go back up here, and we say, okay, well, knowing that it follows a normal distribution, the distribution for the SATs follows a normal distribution with a mean of 1100 and a standard deviation of 200.
Okay.
So it's that special case. And then of course the ACTs also follow a normal distribution centered on 21 with a standard deviation of 6. Good. Okay, I kind of got jiggy with my notes here, so let me just make sure I didn't miss anything or forget to tell you guys anything. There's a lot. Okay. Good. So how we're going to use these is to find areas under the curve. So the standardizing part of it, or part of the question, is only the first step in solving these problems, because usually we want to find probabilities associated with some observation, okay? Which means we're going to have to find areas under the curve. So we find z-scores, or we standardize values in order to be able to find probabilities. In order to be able to find probabilities. So if we've got a normal distribution like this, it's centered on some mean and some standard deviation. If I have an observation here, then we can standardize that value, right? We practiced that already, and we're going to do more practice because these things are kind of tricky. Okay. But then we're also going to say, all right, let's think back. We said that the area under the curve, that's a probability. Okay. And so what I need to be able to do is say, okay, then this area must be the probability of an observation being less than X. Okay. So this is the probability an observation is less than X. It gets kind of interesting because the probability of being exactly X is 0. So the probability of being exactly something is 0. If you think about kind of the area, if you're calculating area in any way, right? It's the width times the height or some version of that. But if there's no width, then there's no area, right? And so sometimes it gets confusing because I kind of flip-flop back and forth between less than or equal to X, but then greater than or equal to X, because at exactly X, there is no area. So now this area here, wanted to draw the lines the other way. This is the probability of an observation greater than X. Okay. Okay. So how do we get from a Z? So, okay, I've already told you we need to standardize the values, which means calculate a Z score. Calculate Z score. Yeah. Once we have that, then what are we supposed to do? Okay, so I've got these very old school tables that I'm going to pass around. I know it irks me to use these still, but it is nice to have. So I had some laying in my desk, so you can have one. Might be nice for when you're working on these problems. Yeah, because what we're gonna do is we're gonna use what we call a Z table. Okay. And the crowd goes wild, I guess. So we're gonna use these Z tables. Of course, this is very, very old school of us, or of me, I guess. Okay, we should be using R to do these things, and the textbook does show you how to do it. But I don't want to force you to use R if you're not comfortable. So that's why I want to just give you the tables so that you have them. Okay. So here on page 136 of the textbook. On page 136 of the textbook, it does go through and it gives you the command for finding the areas under the curve, right? It does the exact same thing as the table, but we're going to use the table. The last option for finding tail areas is to use what's called a probability table. These are occasionally used in the classroom, but rarely in practice. I know, how silly, but that's what we're using. Yeah. Okay, and so, all right, let's grab an example for us to work through. So I want to show you kind of by working through this example together how to use the Z table that you just have now. Okay. So let's see here. Again, we're talking about these SAT scores. So cumulative SAT scores are approximated well by a normal model. And here we're using that normal kind of shorthand, right? They're nice and they tell you that the mean is 1100 and the sigma is 200, which are the same values that we had before. That can change, but in this case, it's nice that it stays the same, right? So now we're talking about SAT scores. So just from this, what I want you to do, as soon as you're doing these problems, I want you to start out by drawing out this curve. And in the beginning, you're going to say, oh, I don't need the curve. I can just find it. I can just solve this problem, right? And that's great, right? But what you're going to find is that the more you draw the curve, it will help you visualize the problem and you can see what you need to solve. So the first thing you're going to do is draw out your normal distribution. Okay. This one, right, because I'm told that it follows a normal distribution. This one is centered on 1100 and sigma is 200. So first thing I want to do is just jot down that information. Now I have it. Shannon is a randomly selected SAT taker. Nothing's known about Shannon's SAT aptitude. So we just want to know what's the probability that is at least 11 90s. Okay. So now we have this, what is the probability? Very different though from the probability questions that we've been solving. All right, so very different. Okay, so now I want to know a probability associated with 1190. So my observation that I'm interested in is 1190. Okay. And because there's only one, we're only interested in Shannon, so I don't need to use the subscripts, right? Probably nice to start with one like this and not with the subscripts, but trying something. So 1190 is above the mean. I'm not going to pay too much attention with where it would be. As long as I put it above the mean, right, then it's just to visualize the problem. So I'm going to draw it here. So X is 1190. And the probability, what's the probability? Well, that's an area under the curve, right? So here, area under the curve. Okay. And then we have to specify which area under the curve, right? This area to the left is going to be the probability of scoring less than 1190, right? But we want to know the probability of scoring at least 1190. Yeah. So here, at least means that this is the area that we're interested in. And usually I put a little question mark beside the thing that I'm going to be looking for just to remind myself. Okay. Because later I'll give you a probability and then you'll work backwards to an X. So we'll kind of be working and solving for different things, right? So then I find it helpful if I put a little question mark just to remind myself what it is I'm looking for. Okay. All right. So if you've had a glance at, oh, there, at the, hey, only one left over. Nice. That's great. Yes. If you've had a glance at this, looks messy, right? It is and it isn't. Okay. So what we want to do is, well, I see a Z on here. Okay. I see Z on here, so that's a clue. I'm going to need to calculate a Z score. We know how to do that, right? So let's start by doing that. So I need to find Z equals X minus mu over sigma. Z is 1190 minus 1100 divided by 200, which gives me a Z of 0.45. It's a nice, just two decimal places. I didn't have to do any rounding. It's almost like they spent some time figuring out numbers that work. Bless you. Okay, so now that we have this Z score, right? Now we're going to use what we call the Z table. So that's the table that you just got, yours to treasure, okay, to find probabilities, right? Which means that I'm going to walk you through what the Z table looks like. Okay. But first, to find probabilities associated with this Z score, we will use the Z table. Now the Z table, let's see here. I've got one here. Oh. Z table looks like this. It's 2 pages. Okay, so let's just kind of get acquainted here. It's 2 pages, and you'll see one page starts with negative Z scores. And then if you flip it over, you've got your positive Z scores, right? And first off, this part, people ignore this part, but it actually explains exactly how to use the Z table, right? But it's a little kind of mystical right now. So let's kind of dissect that together. So here's a Z table. Okay. All right. So let's start here. We're familiar with this normal distribution, and then we have a Z score here, right? And then we're told, okay, there's a table entry. So it helps to know what a table entry is. And the table entry is referring to these values here in the body of the table. So these are table entries. That's a good start. Okay. It says the table entry for Z. Okay, so that means that you need to feed it some Z. Okay, and so Z is going to have 2 decimal places, the whole value, and the first decimal place is in the left-hand margin, and then the second decimal is in the top margin. Okay, so what you're going to do is you're going to match these up and you're going to land on a table entry. So here, this is the whole number and first decimal of Z. Okay. And then this top row is the second decimal place. Okay. So, okay, we're able to feed it some Z score, great, by kind of joining up the first chunk and then the second decimal, and then I land on some value. Okay, so the table entry for Z is the area under the standard normal curve to the left of Z. Okay, so it's only to the left of Z, which it shows here, right? We don't need the area to the right explicitly, right? Because the total area under the curve is 1. So remember, the total area under the curve is 1. So now it's like a puzzle piece, right? So you know the total is 1. If I am told that the area to the left is 0.0012, right? Then the area to the right must be 1 minus 0.0012, for example, right? The table entries are the probabilities. Probability. Technically, the probability of an area less or of a Z score less than the Z, right? Probability of an observation less than Z, whatever Z that you fed it. Okay. So it looks like it's all haphazard, but if you think about your scale, right? Z is centered on 0, right? So as you move in and it starts, the farthest it can go is negative 3.49. That doesn't mean it doesn't continue. It just means that the area becomes super, super, super small, that we stop caring, right? We just say it's extremely small, right? In fact, it's less than 0.0002, right? That's a very small probability, right? And so what this table is when I say area under the curve, if you think about, if you've taken Calc 2, for example, right? Integration is finding the area under the curve. Oh man, we don't want to do that, right? We don't have to. That's why we're using the table, right? So someone at some point decided, oh, I'm so done with integrating these things. I'm just going to go through at certain cutoff points and I'm going to find this area once and for all. And then I'm going to share it with my colleagues and then share it with my students. And then here we are. Right, so essentially what's happening is if you have your normal distribution like this, right, Z is centered on 0, then what's happened is at -3.49, someone has found that the area to the left is 0.0002. If I move on, -3.48, the area to the left is 0.0003, and then it stays basically 0.0003 for a long time, right? And then it moves up, so then it's going incrementally, it's increasing, but in the very beginning, because these tails are so kind of gradual, right? It doesn't increase very quickly, right? And so here, they're not this far apart, but just to visualize 0.0003, oops, right, and so on and so forth. If we go to the positive side of the Z table, Z is 0.00. The area to the left must be 0.5, right? The area to the right must be 0.5, right? So we can leverage that symmetry around the mean, and we can say, okay, 3.49 is where they decided to stop making this table because the area to the left is 0.9998, right? So here at 3.49, by symmetry alone, right, I can say that, okay, well then the area in this tail must be 0.002, or one more zero, I think, 0.0002, right? But the table gives me this area. Oops, there's a page break there. 0.9998, right? But that is 1 minus 0.998. So you can leverage the symmetry around the mean, but that's going to take some practice. Right. Okay, so for our question, we found a Z-score of 0.45. So now we want to find the probability. In fact, we want to find the probability, the area to the right, right above this Z-score. But the Z table gives us the area to the left, which is fine. We can work with that. So for our value, we found Z equal to 0.45. So then that's positive. So I'm going to be on the positive side. I'm going to grab this so I can write on it. So first thing I'm going to do is I'm going to look at the first two numbers, 0.4. And then usually what I do is I'll highlight it. Or if I'm working on the paper, I like to take another piece of paper just so, or a ruler or something. We don't carry rulers around, I know that, but right, something so your eyes don't jump around so much. And then the second decimal is the 5. So then where they join here is 0.6736. That's the probability of finding a z-score less than 0.45. So we can write this out, our findings in words, using the Z table. We find the area to the left, right? It's important to remember that it's to the left of Z equal to 0.45 is 0.6736. I guess not a period yet, which means that the area to the right is 1 minus that, which means the area to the right of Z equal to 0.45 is 1 minus 0.6736, which is 0.3264. Yeah. If you wanted to, you could use probability notation here, right? Or we could write the probability that Z is greater than or equal to 0.45 is 1 minus 0.6736. That's not something I'm expecting you to do, but if you prefer not writing all that out, that's great. Therefore, the probability that Shannon scores at least 1190, that Shannon scores at least 1190 is 0.3264, right? And just to emphasize, I'm gonna just copy this here and put the information on here, because now oops. So we'll do more practice. We'll keep working on the normal distribution, kind of parking lot the geometric for a little bit. If you are up bright and early tomorrow, I'll see you on Zoom. Otherwise, have a great weekend. I'll see you on Tuesday. Hello.